Hello, Professor Lohman. This is test 3, problem number 2. We'll start with part A. This is a long one, so hang in there with me. I'll read the question and then I will start a solution to the answer. Okay, first we will investigate purely vertical motion. The kinematic equations for the vertical motion, ignoring air resistance, is given. Yt equals y naught plus v naught t minus 1/2 g times t squared, where y equals 0 is y naught equals 0, and the initial position v naught is the initial speed, and g is the acceleration due to gravity. Drag the cannonball downwards so it is at ground level 0 meters, which represents the initial height of the object. Then fire the pumpkin straight upward at an angle 90 with an initial speed 14 minutes. How long is the pumpkin to hit the ground? Okay, so here is the simulation. We'll go to 90, 14 meters, launch it. Oh, hold on, it's on car instead of pumpkin. Let's launch it again. No difference. Okay, so we'll start off by writing the equation down. We talked about that the kinematic equation was yt equals y naught plus v naught t minus 1/2 gt squared. This is going to be minus. Okay, so now that we have our equation, we can start plugging in some parts that we know. It's a t right there, 14t. You know that is equal to 0. Minus 9.8 over 2 t squared equals yt. Now we can go about this problem a couple ways. We can either plug it in to the formula opposite b plus or minus the square root of b squared minus 4ac all over 2a. We can plug that's a quadratic formula, we can plug that into there to find the answer. So it would look like negative 14 plus or minus the square root 14 squared minus 4, 9.8 over 2 times 0 all over 2 times negative 9.8 over 2. Put that into my calculator. Okay. 14 minus the square root of 14 squared minus 4 2 times 0 2 times 0.8 2. From that we get time is equal to time is equal to 2.857 seconds. And we got the answer, 2.85. That's correct. So we can move on to part B. When the pumpkin is shot straight upward with an initial speed of 14 meters per second, what is the maximum height above the initial location? Okay, part B. So we can find the maximum height, the time for the maximum height, by finding when opposite of b over 2a. So we have the kinematic equation up there, and we know that b is equal to 14, so negative 14 over 2a, and a is 9.8 over 2, so we know that it's just negative 9.8. 9.8 equals 2a. Divide that to find the time. So 14 divided by 9.8. Now t equals 1.4. 1.428 seconds. So we know the time when the height is at its maximum, so we have to plug it back into the kinematic equation to solve for the maximum height. Okay. Okay. And when we solve that, I will get the answer. So we get y, the maximum height, is equal to 9.999 meters. Okay, you look at that as the correct answer. Okay, now we'll go to part C. Okay, the initial speed of the pumpkin is doubled. How does the maximum height change? Note for this part, as well as later parts, you will need to use the zoom in and out button to see the full trajectory. So we can go about this in two ways. We can use a simulation, or we can think about it. Using our components. So the initial speed of the pumpkin is doubled. How does the maximum height change? So we know the velocity is doubled, and we know that it will take twice as long to reach the maximum height. So we know that velocity times time equals the distance. So we can reason that it will be 4 times greater due to the speed doubling, and we can test that out, and we can see using the simulation what happens whenever it is 4 times, whenever the speed is increased. So we'll start at 45. And then we'll double the speed to 28. So we'll zoom out to see the full trajectory. So we see we can take the stick, and we can measure out the height, and that's 5.61. 5.61. We'll do the maximum height. Okay, so it is around 20. So 5 to 20 is 4, and 4 times is great. So we can see by the simulation that the maximum height increases by a factor of 4 when you double the speed, as we just did. We doubled it from 14 meters per second to 28. So that's done with part C. Okay. So we'll go to part D. Okay, erase all the trajectories and fire the pumpkin vertically again with an initial speed of 14 meters per second. As you found earlier, the maximum height is 9.9. The pumpkin isn't fired vertically, but at an angle less than 90. It can reach the maximum height if its initial speed is faster. Set the initial speed to 22 meters per second and find the angle such that the maximum height is roughly the same. Experiment by firing the pumpkin with many different angles. Okay, so we'll go back to the simulation. We'll do 14 meters per second. You see it reaches that height. Then we'll change it to 22 meters per second, and then we'll test varying angles. We'll start with 35. 35, close, but it doesn't really reach that maximum height. We'll try 40. 40 is really close. That looks like it reaches the maximum height. We'll try 45 for the heck of it. 45 is way over the maximum height. So we can take this, and we can take the tape measure and measure for sure. We can see that these are the same, and so you say that part D is 40. Okay, now we'll go to part E. In the previous part, you found that the pumpkin fired with an initial speed of 22 meters per second and an angle of 40 degrees reaches the same height as the pumpkin fired vertically with an initial speed of 14 meters per second. Which pumpkin takes longer to land? Okay, so it's easy to think that since the pumpkin shot at 40 degrees has a longer range, that it might take a longer amount of time, but it really only is determined by the y component, and the y component has the same height, so the y component for this are equal, so both pumpkins are in the air the same amount of time. Okay, that's part E. Okay. The figure shows two trajectories made by two pumpkins launched with different angles and possibly different initial speeds. Based on the figure, for which trajectory was the pumpkin in the air for the greatest amount of time? Okay, so like we said, the pumpkin is only determined by the y component, and as we see, A has the greatest height compared to B, so A will be in the air longer. You see it's A. Now we'll go to part G. Okay, the range is horizontal distance from the cannon when the pumpkin hits the ground. The range is the horizontal distance from the cannon when the pumpkin hits the ground. This distance is given by the product of the horizontal velocity, okay, which is constant, and the amount of time the pumpkin is in the air, which is determined by the vertical component of the initial velocity, as you just discovered. Set the initial speed of 14 meters per second and fire the pumpkin several times while varying the angle between the cannon and the horizontal, for which angle is the range a maximum with the initial speed held constant. Okay, so we'll test this out. Okay, we'll clear this off. Okay, set it to 14 meters per second. Okay, so now we will do multiple trials. We'll do one at 45, do one at 90, do one at 60, do one at 30, okay, so we found that at 45 degrees that has the highest range, and we can determine that by a lot of factors, as the range has the highest amount of time, and has the greatest amount of time and horizontal velocity, which time in the air, and horizontal velocity, which will give it a bigger range. So we found that it's 45 degrees has the highest range. Do the experiment. Okay, how does the range of the pumpkin change if its initial velocity is tripled, keeping the angle fixed and less than 90? How did the range of the pumpkin change if the initial velocity is tripled? Okay, so if the velocity is tripled, it's going to be in the air 3 times as long. And we can even test this out right here. It's going to be in the air 3 times as long, and the velocity is already 3. It takes 3 times the velocity, and it's going to be in the air 3 times as long. So we can already tell that it should be about 9 times as far. But if we want to test this using the if we want to test this, we could go about it with we could start by deleting this and maybe setting it to 5 meters per second and seeing how it does. Let's set it to 10 meters per second, and then we'll set it to 30 meters per second. And we'll back it up. No. We'll zoom out. We'll take the tape measure. And it's about 9 meters, 10 meters. Okay, and we'll do it with the 3 times the velocity. Okay. So this is about 80 meters. This is about 9 meters. So we can tell that it's about 9 times as great, which is what we get for part H. Okay. Now let's start with part I. Now let's see what happens when the cannon is high above the ground. Click on the cannon and drag it upward as far as it goes, 15 meters above the ground. Set the initial velocity to 14 meters per second and fire several pumpkins while varying the angle. What angle is the range the greatest? Okay. So we'll delete this. Put the tape measure back. Zoom in. Raise this to 15 meters. Now let's test angles by angle. So we'll test 40, 20, 50, and 45. 40. 14 meters per second, we'll put it. Okay. Okay, we did it at 40 meters, 40 degrees. We'll do it at 20 degrees. Do it at 50 degrees. Do it at 45. And we'll do it at 30. As we can see, 30 went the farthest, so it's 30 degrees. We know that by looking at this graph that we know that it stays in the air longer if the y component is the highest. But in this scenario, since we're 15 meters off the ground, the y component doesn't matter as much. So at an angle less than 45 degrees, there will be a greater range. Okay, go to part J. So far in the tutorial, you've been launching a pumpkin. Let's see what happens to the trajectory if you launch something bigger and heavier, like a car. Compare the trajectory and the range of the pumpkin to that of the car using the same initial speed and angle, 45 degrees. Be sure that the air resistance is turned off. Okay, with no air resistance, when we test this, we should find that they move identical. And we know that because we've done tests on like the moon, for example, and we found that a feather and a baseball can fall at the same rate. They fall at the same time because there's no air resistance in space. So we'll test that out right now and we'll see that to be true. We did that with a pumpkin. Now we'll do it with a car. And there's the same trajectory. Okay. We'll move on. The trajectory and the range of the car and the pumpkins are identical. Okay, part K. In the previous part, you discovered that the trajectory of the object does not depend on the object's size or mass. But if you have seen or discovered a parachutist or a feather falling, you know this isn't really true. That it is because we have been neglecting air resistance, and we will now study its effects here. For the following part, select lab mode of the simulation found at the bottom of the screen. Notice that you can adjust the mass and diameter of the object being launched. Turn air resistance by checking the box. Fire a cannonball with an initial speed of 18 meters per second and an angle of 45 degrees. Compare the trajectories to the case with air resistance. How does trajectory differ? Okay, so we know that air resistance, we'll change this to lab. Mark this off. We'll turn off air resistance for one trial. We'll turn on air resistance. Now we can see with air resistance the trajectory was less and the range was less. So that's because the air resistance, the effects of air resistance. Trajectory with air resistance has a shorter range. Okay, but let's see end of part K. Part L. What happens to the trajectory of the cannonball when you increase the diameter while keeping the mass constant? Okay, we'll erase this. So when we increase the diameter, let's do a control, and we'll have it going at low diameter, and then we'll increase the diameter and that should increase the surface area and the area of the ball, which will have greater air resistance against it. And we see that it has the air resistance made the trajectory and range less. So increasing the size makes the range of the trajectory decrease. Okay, part M. You might think that it's never a good approximation to ignore air resistance. However, often it is. Fire the cannonball with air resistance, and then fire with air resistance, same angle and initial speed. Then adjust the mass of the cannonball. Increase it and decrease it, and see what happens to the trajectory. Don't change the diameter. What does this range with air resistance approach to range with air resistance? Okay. So what we're comparing to is without air resistance. So we'll do one without air resistance at a constant speed. And then we'll change the mass. We'll start at a really low mass. And we'll do a trial. This is with a low mass. Oh shoot, we didn't turn air resistance on. So we'll turn air resistance back on. This is with a low mass. See that trajectory and range is lower. Now as we increase the mass, we'll start it at a medium mass. You see it approaches the range without air resistance as the mass increases. We'll do one with the mass at the highest we can have it on this simulation. And we can see that it approaches the trajectory of the projectile without air resistance, which is what we get. The range of with air resistance approaches the range without air resistance as the mass of the cannonball increases. So that has been question 2, test 3, problem 2, and have a nice day.